Hey, we are recording already.
Que es por eso que me siento aquí.
Okay, thank you very much for being here. Today we have the pleasure of having Gastón Escobar as visitor. He did a PhD in La Plata and then moved to Padua for a postdoc, and now is postdoc at the AAC and works in the mini-HAWKS project, which we know very well here. But apart from his scientific CV, it's important to note that you have in front of your eyes a world champion of Truco is a card game, very famous apparently in Argentina, also in Italy because he's world champion in Italy, and I've been told that even in Valencia they play. He is world champion 2024 and second 2025. The title to the top, but it was without training. So I think it's worth it.
He's Italian world champion, like in the US they're world champion of basketball.
No, the Argentinians, they know the world champion of Truco. But the story of how he reached the title deserves a documentary, and if you can, pay a beer to him and ask him about the story. And with that, I leave you with the...
Excellent introduction, thank you. I went to defend the title back last week. I come from there. Well, but here I'm here to talk about the mini-HAWKS project, which is a survey designed to discover efficient black holes. So the main goal of the project comes from the fact that when we want to study the astrophysics of black holes, let's say, for example, if we develop models that, with which we want to know which are the processes that determine the masses, if there is a mass gap between neutron stars and black holes, there are many open questions. All these lines of research have a common bottleneck, which is the lack of data, no? As usual in many other lines. Well, the main goal of this project is to accelerate the rate at which we acquire that data. Which is the problem in discovering black holes? Well, in fact, essentially the problem is that we need to observe the black hole in a very specific situation and moment. No? Let's talk about the X-ray binaries. I will define it briefly. An X-ray binary, this is well, the picture. If you could see in synchrotron, gamma rays, X-rays, and the optical, you would see something like that. But, well, an X-ray binary is essentially a binary system composed of a star and a compact companion that accretes matter from the star, forms an accretion disk. This disk emits essentially in X-rays. And in that configuration, we sometimes even are able to detect black holes. No? So this is the context in which we find the problem to detect them. No? That's why we need to change the strategy. But it is even more difficult than that if we are based only on X-ray data. If we follow this diagram, this is a hardness intensity diagram. Hardness is essentially the slope of the spectrum in X-rays. And this is the intensity in X-rays. No? So usually what happens is that most of these systems are accreting at a level in which the X-ray emission is lower than the detecting threshold of the current instruments. So they are there, but we cannot detect this X-ray emission. And they are, let's say, in this state, this is a hard state, but with low intensity. Hard state means that the emission is dominated by the hardest part of the X-ray, no? And analogously in the soft state. So sometimes these sources enter into a state that is called an outburst, and they rise their intensity by many orders of magnitude. Then they shift to a softer spectrum, and in a scale time of months, they slowly go back to the hard state and lower intensity. What happens here? There is, during this moment in which we have the more probability of observing them. With all this scenario, in the last 50 years, when the X-ray astronomy started, we reached to observe around 70 X-ray transients. It's the way which we call these sources. Huh? So, and moreover, even observing them is an indirect, could be an indirect indicator of the presence of a black hole. It's not a confirmation. In order to know that we have a black hole in that system, we need to know, for example, the mass function. No? When we know that, we say that we have a dynamical confirmation of the black hole. So, up to now, we have 20 confirmed black holes from these around 70 detections in X-ray. So, what's the problem? Well, the problem is that if we want to have a robust statistic to confront with the models, we need to increase at least, let's say, a factor of 10 the number of sources that we detected. If we follow the rate at which we are detecting currently these sources, we will need to wait 200 years in order to have a factor of 10 new data. So this is the main motivation which we need to change the strategy or develop a new strategy to discover black holes. Good. And that is why the HAWKS project arises. So what if I told you that we can find black holes using only photometric data? That's the idea of this project. So how do we do that? The project exploits the fact that when we have an accretion disk that is surrounding a black hole, the H-alpha line will be very broad as an indicator of a strong gravitational field. And well, with a blind survey like this, we plan to say sample 3,000 square degrees in the galactic plane, and this will deliver 100 new black holes in just a few years. Well, so we mean an acceleration of the detection of black holes. No? Instead of 200 years, we are talking about a few years, changing the strategy. Okay. So, how is the method? Well, the method starts from 3 specific filters designed specifically for this project, which are 3 filters centered in the H-alpha line with different widths. And they are installed in the set in the Observatorio de Javalambre. We have already used the filters to observe 4 fields up to now. But well, let's talk about the method. Sorry. So with these 3 filters, we managed to recover 2 properties of the H-alpha emission line, which are the full width at Hubble maximum and the equivalent width. But particularly with the full width at Hubble maximum, you know, this is the reconstruction from the fluxes that we measured, essentially. So when we know the full width Hubble maximum, we can use a correlation that was studied by Jorge Casares 10 years ago. And with this correlation, we can recover from the full width Hubble maximum the semi-amplitude of the velocity of the companion. With that, if we have information about the period, let's say from a light curve, we can reconstruct a mass function. This is the equation of the mass function. It does not look like the original equation of the mass function, of course, because they are already, we have already replaced the correlations that we use. But the important thing to see here is that if we start from the full width half maximum and the Rayet period, well, we need the distance there. So we can recover the photometric mass function. Sorry, this is days, unit of days. So with this, if the photometric mass function is at least 3 solar masses, we are in very, how can I say it? We have a very good candidate of a black hole because the mass function is a lower bound to the mass. As up to now, we haven't seen, for example, neutron stars that reach 3 solar masses. So having a photometric mass function of 3 is a super strong indicator of a black hole. That's the method. And as you see, we started just with photometric data. There are 3 fluxes in the 3 filters, and if we manage to recover this data from these 3 fluxes, we are able to find potential black holes or candidates. Good. So that was the idea of HAWKS, but what we are doing now is called mini HAWKS, which is essentially the proof of concept that HAWKS will work. So instead of mapping 3,000 square degrees at once, we are mapping 50 square degrees just to prove that the method will work. And we have already 400 hours guaranteed of observation that will be carried during 2 more years. And well, with those observations, we expect to have many, well, light curves of 14 hours. There are thousands of H-alpha meters that will be interesting. Among them, one of the most interesting sources that we will find are cataclysmic variables. Then there are other H-alpha meters as T Tauri, the stars, carbon stars, Mira variables, and so on. All these sources for us are contaminants, essentially. We have to develop a technique in order to separate these contaminants and have only the best candidates that we have of black holes. Excellent. So, what I will show you, when I show you the results, I will show you about this field that we observed. It was the first one that we observed, was the commissioning field that contains the M71 cluster here. And we chose this field in order to test the technique in the situation in which we have a very crowded field. Since we have very crowded regions, we chose to use PSF photometry. Okay. This is well, the approach is for the approach is with PSF. We use DAOPhot, and there are 2 products that we obtain with that. We use stack photometry in order to reach maximum depth possible, the maximum possible depth, and we also use all frame photometry, which will allow us to reconstruct light curves. Okay. Good. So I will show you before the results of this field. How is one of the main tools that we use in order to separate the contaminants, which is the H-alpha color diagram. So essentially, it's a color diagram with the 3 filters in H-alpha. The 350 minus 150 and the 150 minus 35. So I didn't mention it before, but the widths of the filters are designed specifically to see the features of the H-alpha line. I mean, this one is essentially at the core of the line, and so on. We can recover the features at different scales. Good. So this is the color diagram in H-alpha, and I will show you how we will look at it for different populations. And with this, I will show you how this diagram could be used to separate efficiently the contaminants. Well, this is the sample of the 20 black holes that we have for now. So, as you can see, these curved lines are lines of constant full width Hall maximum, and the horizontal lines are lines of constant equivalent width. The black holes usually shift also to this region because, in fact, over 2,200 is a number that we take as limit. We are talking about very broad lines, which is, in fact, an indicator of a strong gravitational field. No? So, it is not surprising to see black holes here. There are also, other black holes here. It's okay. But this is the hot spot of the diagram. This is where we will find our best candidates. These are field stars. No problem. These are, for example, T Tauri and B stars. They are alpha emitters, but you can see that they follow this line of full width Hall maximum at 500 kilometers per second. Okay, not so broad to contaminate too much for now. If you include flare stars, they will appear over 2,200 kilometers per second, but this is an artifact of the filters, because if you follow this spectrum, these are the transmission curves of the filter. Okay? Imagine that you don't have this emission line for now. You have this continuum. The filter interprets this part as a broad emission line. If it's like we would have a base, an imaginary continuum base here, and then this is the broad line. That's why the artifact provides a source that apparently has over 2,200 kilometers per second, but it's an artifact, it's not real. But of course, with spectroscopy, we can define completely. Once we have the candidates, with spectroscopy, we define completely the nature of the source. Hopefully. Well, sorry, we were on T Tauris, V stars, flare stars. Now, cataclysmic variables. The cataclysmic variables are spread usually all around this diagram, and they are other population that may enter in our region of most interest. Because, well, maybe I think I have this information here. Yeah. So, there are some cataclysmic variables that will enter in the region that we are defining as the most interesting. But there are certain conditions in which they can enter at that region. And that's why we are also able to discard them as potential black holes. The cataclysmic variables that will enter here have the particularity that they have short orbital periods and high inclination, so they are eclipsing. So at this point is when we also will require to do a variability analysis in order to filter the best candidates. So the strategy is supplementary in these senses. The color diagram is one way of filtering the sources, and the variability analysis is a complementary way to filter also the sources. And after those two steps, we arrive with the very best candidates that we have. Good. So, coming back to this, to the results of the M71 field, all these diagrams that I showed you were real spectra, but with colors computed synthetically, with the transmission curves of the spectra filters. Now, this diagram is the color diagram of the field. So, This is the color diagram of the field. And as you can see, there are many sources that fall in this, the most interesting region. And there are other sources around here that also deserve some attention. In total, we have 20 sources that are interesting in this sense. Interesting in the sense that they are H-alpha emitters that could be or potentially black holes or other type of source as contaminant, but also that deserves classification. Right? No. From these 20, and I want to emphasize that from the field, we started with 700,000 stars, and we ended with 20 candidates. So that's the how we want to show the efficiency of the technique in that sense. We filter from the 700,000 stars, 20 candidates. Good. From these 20, there are 7 that are already known, that we found through a cross-match of different catalogs. There are 3 Mira variables, 1 carbon star, 1 Wolf-Rayet, 2 cataclysmic variables, and 13 unknown interesting sources, which are the crosses marked in blue. From where maybe there is a black hole. I mean, no, it's a. I mean, I always say maybe because in the sense of the population studies, it's more probable to find other type of sources, of course, because of the number of sources that we have. For, let's say, for every hundreds of cataclysmic variables, one would expect a few black holes, let's say, in a populational sense. Good. However, they are strong candidates. So what do we do now? Once we have this, we start to make a follow-up spectroscopy and try to confirm the nature of these sources. The first that we did is to confirm the sources that were already known. For example, well, we did that with the GTC and NOT telescope that are telescoping the island of La Palma. Let's start, for example, we made this follow-up spectroscopy of these 2 cataclysmic variables, and we have this spectra. Well, maybe you can see the double peak shape of the line. This is characteristic of a accretion disk. No? Essentially, the line splits because we have a part that is going on that side and in that sense, and the other part that is going like this. So, well, we performed also that with the Wolf-Rayet star. There is a carbon star there. There are 2 Mira variables that are interesting contaminants in the sense that these are 2 different sources, but the Mira variables have the property that they can follow different, they can appear at different parts of the diagram at different moments. No? A demonstration of that is that if, depending on the moment in which we observe a Mira variable, we can see an H-alpha line like this, or we can see something like this. So these are 2 different sources, but it could also be the same source at different times. Well, let's go to the most interesting candidates. So we have for now followed 4 candidates from the sources that we didn't know before. These first 2 that are in the hotspot, in the most interesting region where we will find new black holes, well, they are chromospherically active stars. It's okay. It could happen. We still put an interrogation sign here because, well, I'm not an expert in the spectra. I mean, if I see this spectra, I cannot for sure tell that this is a flare star. I don't know. I don't have that knowledge. Just from the spectra, to arrive to this conclusion, but someone else did it. Of our group, of course. We have Manuel Torres. Well, and these are these other two that, well, they are not in this most interesting region, but it's what we reach to do. And there are other two stars that present flaring activity. So, what I wanted to show you was the strategy. This is a project that just started a few months ago. But it's being planned since a very, very long time. And well, this is the strategy. No black holes yet, but we expect to find with some luck 1 or 2 in these 2 years. But 1 is enough to prove the concept. If we have 1, we are done. We are ready. No. We are ready to prove the concept. So, what are we planning to do for the next time? We are including the variability study, which is my part. I'm a recent postdoc in the group, and I'm starting with the variability study and developing a program to study the variability, a code. So, when we continue with the follow-up of the candidates, and at the long term, once the techniques and the codes are proved, we are thinking to include machine learning algorithms to classify the light curves. And well, with this will end in August 2025 with the legacy survey. We will public catalog, and at that moment we are also planning to do a workshop to present the catalog of the mini holes, but it will happen in 2 years. Okay, so I'll let you with the summary, and happy to hear some questions if you have.
Thank you very much, Gastón. Questions?
I have a couple. I understand that you follow up objects that are not candidates, clear candidates for black holes, in order to let's say know your enemies, no?
Sure.
To characterize well how different species can.
Yes, but because it is also useful for many lines of research. I mean,
sure.
We have contaminants that they are not essentially the main goal, but in the meanwhile, we can also classify other sources that may be interesting for other lines of research. So we are doing that also. Even if we expect to find 1 black hole, in the meantime, if we can classify hundreds of cataclysmic variables or Tauri stars and so on, we will do that, of course. Yes, that's why we do that.
Okay. Yeah, okay. Actually, I have 2 more.
Go ahead.
Okay.
He was shocked, so we are.
Yeah, so what is the filter that you use for the variability? I mean, you check the variability in what filter?
We use the 3 filters at the same time, but yeah. As you know, when you reconstruct a light curve, I don't have a plot of a light curve here, but the different filters will show a jump between the light curves, no? But we can fit that jump using, for example, PSF stars that are usually constant. So then you know how the filter jumps from one flux to another, and then you use that constant for other stars. Other stars of the same or similar spectral type. No? So in that sense, we can recover light curves of up to 120 or 140 points along 14 hours. So that's why we try to use the 3 filters for the light cover. Otherwise, if we use 1 filter at a time, we would have 40 points per each light cover.
Okay, so you are going to all the filters are normalized to use like a single.
Yes, like it was a single type.
10 series. And the last question,
Was
if it's possible, can you show again the log curves of the black holes in the what you expect to have the black holes with the observed black holes?
but
Yeah, this one, for instance.
okay, this one.
So it's not. I mean, for somebody that is not not familiar with that, from the observed black holes, it's not that clear that is that obvious that this is the region with you have more observations. So I understand that you are focused on that region because it's where you expect to find more, and like there is a bias on the observation that you find more. You find also in other regions. But I don't know. Just
Well,
my question.
no, but good. This, in fact, I should state it in the opposite sense. This is a region in which we expect the less contaminants, not more black holes. Sorry, maybe I told that in that sense, but the very meaning of this is that, as you can see, they are almost alone. The black holes that are there are almost just black holes. That was the idea, and in particular, Jorge Casares made Monte Carlo simulations in 2028, and he showed it that we chose this region, we can discard 99.9% of the cataclysmic variables that are most of the contaminants, and we accept almost the half of the black holes for them. So that's we tested this how efficient was to choose the region in that way.
Thank you.
Also, a couple of questions copying from Michael. Keeping on this plot, what is the impact of the inclination of the system on your detection? I would assume that the more edge on, the higher the full width and maximum, the easier the detection.
Well, for the filter for this one of the 350, I should say that I would say that yes, if it's a wider line, it would be easier to detect for this filter. But I cannot now on the fly tell you how is the dependence on inclination on that. I should see it more carefully. I cannot tell it on the fly. No? Sorry, but if you want to have one comment about that particularly.
I was just curious.
Okay.
It felt in my brain. It felt very, very natural. And I had another question, but I forgot. So I'll wait for the others to ask questions.
Okay.
I was going to ask that the cataclysmic variables that enter the region would be eclipsing, but the black holes could be eclipsing too. So then would it be a matter of they would have a shorter period or certain features?
The black holes, they could be eclipsing too, but well, that's when the variability analysis enters in the classification, because when you have the period and accounting for the fact that we have a full width maximum already measured, it's value. With these two data, you can recover the mass function. And the mass function will tell you, in fact, if you can tell this is a black hole, or if it's much lower, most probably it will be a value.
What I mean is, the fact that they are eclipsing wouldn't mean that you discard this candidate. You will still need to calculate the mass function.
Well, you can discard them also by the shape of the light.
Yes.
I mean, if they are eclipsing, you can use the fact that you know the shape, and you use that to discard it as candidate.
And I wanted to reply to something I said, because if the accretion disk is flaring on the edges, you might cover up the region where the H alpha is wide,
Yeah.
if it's very edge on. The edge of the disk, if it's flaring up and if it's getting thicker on the edge, if it's very edge on, it might hide the central region where the H alpha might be a wider one. So that may explain some of the not so straightforward dependence on the inclination of the system and the width of the line.
I see.
Well, some dependence is there, no? Because this move
Yeah.
there when they have high inclination.
Shift forward, yes, this is the.
Yeah. As Israel said, like the more edge on, the better. Like, it might reach a point where it's more edge on, but then you don't get the widest region.
More questions? Alejandro?
Enough. Oh, no, you go first. I was going to say enough questions about the Milky Way. So if you have a Milky Way question, you
Yeah. About all this in the Milky Way. So in this figure, there is no Mira point. So that was not expected. Miras was not expected as contaminants.
Well, I think they were expected, but they are just not added here. Okay. Or when this
But
plot,
hard to predict.
but well, I took this plot is from 2028,
Yeah.
but 2018, so
Yeah.
from the future. Yeah, but yes, we expect them not to contact.
Okay, now. No, the Milky Way. Sorry, thank you for the talk. It was very interesting, but I'm going to go off very far away. High redshift actually. I was going to ask about possible contamination by quasars or emission in galaxies or etc. I only see it goes down to 500 kilometers per second.
This is because you read this line.
You remove them with that. Okay.
No? No, I mean, you asked this because you
No,
You saw the
I'm
AGS
asking
here.
this because this is the only thing that I was thinking about when I heard about the mini book.
No, it's okay, it's okay. So, yes, they are contaminants, in fact,
Okay.
but we expect them, let's say, for example, the AGNs, we expect them to see very at the right part. So, with that, we can not exactly discard them, of course, because until we are sure, we maybe need to make it a follow-up spectroscopy. But they are indicators, not, I mean, I'm talking in the case in which we don't know even if there is an AGN. No? I mean, you have a source there, and the fact that it's very red could be an indicator that it's an AGN, but it's not, of course, a conclusion. No? But yes, I didn't mention them, but they are contaminants too.
I can also answer that because when this was starting, Jorge asked me about the density of aliens. I don't remember the numbers, but the density you expect from interlopers was very low to have like a high number of interloper agents falling exactly in the narrowest filter.
Yes, but
Well,
it is true. It is true.
Yeah, you can have some, but they were very few.
Yeah, no, it's true that the white thing. I was checking, and there are a few, but it is true that there are very little. I guess you have to take into account the equivalent width, etc. But
So to have contamination with such full width,
that is the
you
problem.
need H beta to come there, or even some helium 9 from there. I did the numbers for the lightest ones, and the number density was very low. So the chances, if on top of that you use a color criterion, I guess you.
Yeah, I was mostly thinking about what can you find rather than what can contaminate your region.
That's
It is-
another thing, the spin-offs of mini HAWKS.
That was
That's
mostly
part of the spin-off.
because I was wondering in the actual plot that you have with the data that you have now, where would they be? Because I don't know if you have cross-matched some of the sources with like this, for example. Because I'm wondering, for example, in the part at 0.3 or something.
Like
Yeah.
here.
No. Left. At 0 in the x-axis and 0.3 or something in the. That is not 0. That's 0.25.
left.
0 in the x-axis.
I was taking this as 0. I don't know what.
Because I'm wondering if some of those are actually AGNs with the emission line in the broad, in the intermediate H alpha filter, but not in the narrow one. Does that make sense? I'm sorry, I'm just.
Oof.
Doesn't
no.
matter. This is not important
No,
for the work. I'm just looking at the plots and trying to.
I think we should think about it carefully, but there is also the fact that because of the redshift, there is the line that is moved from its center, and maybe the interpretation of the fluxes that the filters receive is different in that case.
That's what I mean. Yes.
But well, I didn't work on that interpretation.
Sorry.
But yes, continue, please tell me.
No. That's what I was meaning. Like in the x-axis. So that, if I'm understanding correctly, this is a color. Is this a color?
This is the color between.
Magnitudes, no?
This is the difference in magnitude.
Magnitude, no? So that means that the higher you go, the it takes me a while to always. It means that what is the 35 one is brighter. No?
As if you go in this direction.
Yes.
Yes.
35 one is
Broader,
brighter.
this is narrower.
You see,
So it means it's brighter in the narrower than in the broader, means that the line is within the narrower and the broader. No? But if you go the other direction, it could easily be that the line is in the broader and the narrower
Because it
has
moves
no
on-
line.
Because of the redshift, you say it
Exactly,
moves,
exactly.
and
Exactly.
okay.
So that's why I was looking at the other
So that's why you expect it to be around here.
below 0. If it's and that would be much more likely because it's much easier to land somewhere in the 150 that is not the 35. Sorry, I'm just.
I see.
I should
No,
be
but
discussing this.
I have one more comment on that. Once we made a calculation about how much we will require to be the velocity of the source in order to escape from the narrowest filter, and we obtained a velocity of 800 kilometers per second.
Oh.
So for galactic sources, this is not a problem. But in fact, for the sources that you mentioned, maybe, I don't know at which redshift you could reach that velocity.
Oh no! This is a different emission line. This is not H alpha. This is like carbon or magnesium or something. And this is in a very narrow redshift range. That line falls within some of the filters. I'm sorry, but this is what happens to me. When
Another way to ask the question is, have you checked each of these spikes?
Yeah.
Are populations share some characteristic or?
They are stars.
Yes.
That's it. If I have to tell in one phrase, the answer is that they are stars. But I think that the discussion was, could there appear an AGN there? Well, I think it could happen, but the things I show here, they are stars.
You could use the same simulations you use this to predict how a quasar would move.
In fact, we can include that in the Monte Carlo simulations that Jorge started.
Just to identify what is the locus where you would expect those sources.
Since I remembered the previous question, I'm going to ask another one using this plot.
Okay.
Because you basically started to look at all the interesting unknown objects. Now, if I had seen this, the first two objects I would have observed are in fact the two you did not.
Well, this happened before I arrived. So before I started my contract. So I don't know the exact reasons, but I know that we tested these two. Well, they are very good.
Those two ones is like, I was like, now he's going to show those two, right? Now he's going to show those two, the ones that in the middle.
I think I don't remember the reason exactly. These DDTs were already being observed by the time I arrived, but there is a color reason about this, by which that I don't remember exactly, but for which we decided to test with this before. Okay, but there is a reason. It's not like we said, well, okay, let's choose not the most interesting, the other. No, there is a reason.
I thought you were just.
Yeah.
Well, yeah, because I have here I don't have the magnitudes themselves, but that's the color. But
I thought you were. As the talk was going on, I was like, and now I'm going to show you the paper we submitted to Nature.
No, it's but we have 2 years more to reach to that maybe.
The question I had from before is the LSST is now in commissioning phase, and LSST does magnitude 21 easily, and also in the plane of the Milky Way, they claim, and is supposed to provide light curves in 6 bands over the next 10 years. Is it going to be any useful for this project, both in terms of variability and color?
Depends. It will be useful, yes, for a cross match and to maybe have more information about the nature of the objects, for sure. But the main part of the technique depends on these 3 specific filters.
My question was in the direction of support, like
yes.
in that variability and these kind of things.
In that sense, for sure, we are. In fact, when this data is available, we're going to do cross match with that. But for now, we have cross match with CTF or with the WISE and so on.
Yes, the idea I guess is to, with this problem that you have, the mini HAWKS, to use that for making the technology. And so to make that test in a crowded global cluster.
On purpose to test the technique with output.
Interesting.
Because the survey is planned to be on the galactic plane, so we expect crowded regions.
Are those observations over, the ones of the follow-up, or
which ones?
The follow-up observations, the spectra are over, or the campaign, or is still?
We are still on the campaign. I mean, I think for the we reached to observe these 2 and these 2, and maybe for the next time we can choose these 2 and see what happens.
Yes, please.
But we are still doing the campaign. Yes, and we have also this is a commissioning field, the one in which we first tested the technique, but the observations already run 4 more fields in which we can reproduce this color diagram and have new potential sources. So we have still a lot of data to test, but first we have to firmly establish the technique with this commissioning field.
One last question. Are these also Miras? Or these are just normal stuff?
Normal stuff.
So why are they here? Because these have chromospheric activity, or?
I understand that, no.
But they have some broad thing in the spectrum to be here.
I would say it's also an artifact. But I don't know, but this is
There are,
if you
there are,
follow,
yeah. This is an M5.
for example, but yes, because this is the line of the main sequence. Essentially, if we put the main sequence in this plot,
Okay.
you follow this line. So these are the stats.
Maybe that's why you didn't choose this one.
Because they reach to the line of the K stars. Well, I think they're kind of far because, for example, this line shows 99.9% of the main sequence stars.
Okay.
So the probability is low, but still, who knows? No, but
Okay. There are no more questions. We thanks again, Gastón.
Yes.
thank you.